All right, welcome back. I'm your host, Ted, and today we're going to continue to make a game on the Mac platform from scratch using kind of minimal libraries, mostly a handmade kind of process. So, the other day we had set up a window, and we also set up a content view inside of that window, and we kind of started to get ready for porting or for doing some metal commands. So you can see here in our code we've got a metal device that we created, metal kit view that we then also created, and we set that as the content view of the window. So now we've kind of got that basic metal set up, but the question is, what do we do once we have that, right? So now we actually need to start drawing some things into this content view. So how do we do that? Well, to get those drawing callbacks, we have to start looking into the documentation. So we're going to look up MTKView and read that documentation. And we're just trying to figure out, okay, how do we get to the thing that's gonna where we can do the drawing, right? So there's one function that we can use to draw into a metal kit view, and so this would be it. It says drawing the view's contents. So when the view needs to update its contents, it calls drawRect method, and that method has been overridden by a subclass or drawInMTKView on the view's delegate if the subclass doesn't override it. You should either subclass MTKView or provide a delegate, but not both. Okay, so it's kind of a lot of object-oriented stuff to sort of imbibe or think about. There's this idea of a delegate object. So let's nuke this. So delegate object. This is actually something that we have done before. Remember this? So in an MTK view, we have to create a delegate object that is then going to, well, that's my preferred way of doing it. You don't have to do it that way. I just like to do it that way because it involves no inheritance, basically, or minimal inheritance. So we don't have to inherit all of MTKView in a subclass. We can just inherit NSObject, the base class for any kind of object in Objective-C. So a delegate is kind of, the word delegate means like somebody or something that you have do your dirty work, right? So it's kind of like a slave to you, or it's a thing that does something for you. So you can think about this as this window here. It has a delegate that handles its window will close action. It's like a little worker bee that will just take care of this window will close callback. So it's not the window that's doing it, it's this separate object called the game window delegate that will handle the window will close. And so that's kind of this, that we could call this a design pattern. The design pattern here is it's called delegation, or say, you've got one object that it kind of does its kind of its own thing, and then you have it delegate other tasks relating to its state out to another object. So this sort of a design pattern is actually very, very common in Objective-C and in Cocoa. So we're not really going to use it that much. We just kind of use it for doing operating system level stuff, but it is kind of important to know what it is. So the idea is we have to create some kind of an object that then implements the method that is a part of that. It's called like a delegate protocol. So here we have game window delegate is an NS object that implements the NS window delegate protocol, and the function that it in that protocol that it implements is this window will close function. So we're going to do a similar thing with the MTLKit view, because you notice that we create this thing, then we set it as the delegate of the window, and then it just kind of takes over and handles that event, right? So we're going to do a similar thing here. We're going to declare an interface for the MTLKit view delegate. So we'll call this MTLKit view delegate, and it's an NS object. And the protocol that we have to look in the documentation to figure out where this protocol is that this delegate implements. So I'll show you how to look in the documentation to do that. So you see draw in MTK view, and I think what this is going to do is it's going to take you to, okay, so if you click on the link, it actually does take you to MTK view delegate. So that's this thing right here. Now, this is actually the function. So documentation MTK view delegate. And you'll see here this is a protocol. So a protocol is kind of like a contract of functions that an object has to implement. So in this case, if you say something implements the MTK view delegate protocol, then you're agreeing that you're going to implement the functions that are a part of that protocol. You don't have to implement all of them. Usually you're given a choice. However, with MTK view delegate, you do have to implement both. So you can implement both. You can implement one of them as a stub if you want to. You don't actually have to implement, if you're just playing around with prototyping a game, you don't really have to do all the detail work right away. You can kind of do it piecemeal if you want to. So we're going to do MTK view delegate. Okay. And then that's just the interface for MTLKit view delegate. And then the implementation, okay. Okay, that's that. And in the implementation, we just got to implement those two functions, right? So we have two functions. We have draw in MTK view, and that's this one. I'm just going to copy that. Okay. We've got this other one. Let's take a look at the other one. Drawable size will change, right? So drawable size will change. Okay. So I think this one actually gets called if you resize the window, right? So remember we have a window, and then inside of that we've got a view that we've got an MTK view. Now if the window changes its size, then I think this thing will get called. And basically what that's telling you to do is, hey, if you have any logic that depends on the size of the window changing, or the size of the viewport changing, hey, the viewport's about to change, you need to update your viewport into metal so that it will draw things in a different kind of a way. That's more or less what this is. You don't have to implement this right away. If you want to just not implement that, you totally have the option to wait. I think for most of the development cycle of a game, you can just not implement that, or you can implement it as a stub like here, because you basically would have to have a resizing window for any of this to have any relevance. So if you don't, at least put a stub in, then the compiler is going to whine at you. But if you can just put in a blank stub. So this right here is actually the really important one. This is what we care about. This is basically, this is the game's rendering loop. So this function right here, drawing MTKView, is going to get called like 60 times a second. And every time that this function gets called, what we need to do is set up some kind of drawing, right? So we need to actually tell the system to queue some commands into a draw buffer or into like a render encoder. There's actually a ton of stuff that we got to do. And I'm actually going to kind of work backwards from just drawing some triangles, and then hopefully a lot of that can kind of we'll see how that goes. But as I said, there's quite a lot to do here, so we'll see how all of that goes. This thing gets called 60 times a second, so that's where we're going to be doing the updating and rendering of the game's logic. So most of your game, most of the cross-platform part of your game is going to live inside of this draw and MTKView method callback. So now that we have this thing here, and it's not necessarily doing anything, we just want to, just as we did with the game window delegate, we want to do a similar thing here. We want to actually just like create one of these things. So we want to do MTKView delegate star view delegate alloc init. Nothing fancy here. We're just creating one. And then what we're going to say is the MTLKit view. Oops. We're going to set the delegate to view delegate. Now, this, first of all, we can see if it compiles. So see if that compiles. See what we get. Oh, that's right. I called it something else. I called it what? MTLKit, yeah, MTLKit view delegate. There we go. I'm just going to call it metal view delegate. I don't really, yeah, whatever. That's fine. Call it MTLKit view delegate. All right, so this is our view delegate thingamajigger. Yeah, so now we'll try and build it again. Okay. Just a bunch of things being okay. So yeah, I just need to use the same case everywhere. No big deal. That's fine. Build again. All right. Okay, that builds. Now I don't know if anything actually changes as a result of running this thing, so we can just like run it real quick just to see what actually happens here. And yeah, it might actually not be anything here. So we'll just see. Yeah, nothing actually changes just by using the metal view delegate. Although we could probably confirm that we're getting called, so that's kind of a different thing. Now, I don't think we're going to do that quite yet, because we probably are getting called. There's so much to go over here that I kind of think the best thing to do is to just kind of get moving with it and set up kind of the basic outline and start to explain it. The first thing we're going to get put into place, I think, is going to be triple buffering. So what triple buffering is is it's a way of telling, it's kind of like a way of, it's a way of holding on to, so well, I guess in order to explain this, we have to talk about vertex buffers for yeah, game objects, geometry, right? Basically, the way that a lot of these modern kind of rendering languages work, this would be the case with OpenGL. It's also the case with DirectX. Pretty much any of these. The kind of an API that you have for most of them is you create some space in memory that represents all of the points on all of the points on the triangles that are going to get drawn. So we call that a vertex buffer. So you're just drawing a bunch of geometry, really, or you're telling the system that you're going to draw a bunch of geometry. So if you're ever drawing, say, even just like a square, like a rectangle, what you're actually doing is you're putting two triangles together, and then you're filling in the triangles with a texture, or you're filling the triangles in with a color. Obviously, if you're doing three-dimensional geometry, then you're allocating a big space in memory that represents all of the vertices on a face. So if you could think of, like a cube, for example, it's the vertices on the front face and the side faces, all of those vertices. And then what you end up doing is you pass those vertices over to the GPU, and that's what it uses to actually draw, or it fills in the colors inside of each of those faces in a process that's called rasterization. So the way that we're going to tell this system what to draw is by giving it a big space in memory for all of the triangle vertices that it's going to then draw. Now, you might think one buffer for this, is that, 2 buffers? Why? So what triple buffering actually refers to, triple buffering refers to the idea of not just having one active vertex buffer at any given point in time, but actually having multiple of them. And there's a reason why you may want to do that. Ultimately, what it comes down to is you can get better performance if you have multiple of these vertex buffers in memory at the same time, and if you have a rendering system that can separate that, can draw from a different vertex buffer than the one that you're currently writing to. So if, for example, if you only had one buffer, right? So like, let's just do a little thought experiment. What if you only had one vertex buffer, right? Well, what does that look like? Okay, so what I'm going to do is I'm going to draw I'm going to write all of this triangle geometry into this vertex buffer, right? And then what I've got to do is I've got to go and send that information off to the GPU. And then the GPU's got to use that information to render the scene, right? It could either be something very complicated, or it could just be two triangles next to each other, like a square on the screen, a flat square on the screen. It could be really anything. The problem is, I have to wait until the system is done drawing that triangle or that quad or all of that geometry before I can write to it again, because I've only got one buffer. So you're not going to get very good frame rates if you have to wait until the system's done drawing. So you can imagine I fill that in like just one buffer, and then I say wait for vertical sync on the monitor, and then it hands me back control, and I start filling in this vertex buffer again. Okay, well that's not going to be, that's not going to have good performance. You could also just start writing to it while it's being displayed, which that really sucks, because then you just have very incorrect data, right? If in the middle of and if the GPU is reading from a buffer while at the same time you're writing from it, well, that's going to be an inconsistent presentation because data from the previous frame or data from the next frame is getting mixed in with data from the previous frame. So one buffer is either slow or bug prone, and we don't want that. So it's much better to actually have multiple of these buffers. Some of these systems have 2 buffers, some of them have 3. Apple, more or less, I think some even have as much as 5. Apple basically suggests that you have 3 buffers. You have 3 Vertex buffers, and that you have the system read from those 3 Vertex buffers. That way, when you're writing to one of the Vertex buffers in your update loop, the GPU is reading from one of the other ones. So the idea is you're always kind of ahead by 1. You're always ahead of the GPU by at least like 1 of these frames, and there's no there's really never any overlapping. It never is the case that the GPU is reading from your buffer while you're writing to it, and you get the added performance benefit. So it's kind of an optimization along the lines of using a little bit more memory in order to not have to use as much CPU, or in order to not have to wait for a process to finish. That's kind of what the thinking is. So how do we do that? Well, in practice, the way Apple suggests you do it and the way that I've done it, I'll show you how I've got it going in one of my game engines. So we'll look at kind of a more finished Mu Solutions platform layer on the Mac. And the way that I'm looking for K frames, something. I'll find it. I'm sure I'll find it. We're gonna use a thing called a dispatch semaphore, but I'll start getting into a little bit of that. So you see that your MTLKit view delegate eventually gets to have kind of a lot of this stuff in it eventually. Okay, yeah. So we're gonna use a dispatch semaphore, and my best understanding of semaphores is what they are. Is if you have a lot of if you have a process that is going to run a lot of many times, or that could seem unbounded in terms of how many times it is going to run, what this does is it lets you say, I'm trying to think of like a good way to describe it. It's almost like a queue. It's kind of like a queue. So, except the idea is that there's a limited number of things that can be waiting in the queue at any given point in time before you allow more stuff to go into the queue. So, let's say that I've got one thing that goes into the queue, right? Like one person enters into the queue, right? And then that person's kind of waiting, or like there's work being done, right? Or there's work about to be done on that person. And then I've got another person that comes in, right? And then I've got a third person. There's 3 people waiting. And then what I say is, okay, once we hit 3, then no more people can come into this thing, or like no more, like we're full, right? So it'd almost be like waiting in line. I don't know, like imagine, like maybe like the Soup Nazi episode from Seinfeld. Like maybe the Soup Nazi is like really just hates having a restaurant that's too full of people, and like once too many people get in line for that at that restaurant, then like his soup lady outside, she starts screaming at people and telling them to go away. It would be kind of like that. So it's kind of like an angry Soup Nazi that just doesn't like to have too many people in his restaurant. And so in this case, the customers are draw calls, are draw events that we're going to actually schedule on the GPU. And in this case, we don't want to have there be any more than like 3 of these kind of waiting to be served or waiting to get drawn at any point in time. We don't want more than 3. And that's kind of what a dispatch semaphore does, is it allows you to control how many of these things are allowed to stack up, how many calls into this draw and MTKView function are allowed to stack up. And the way that you say, hey, wait a minute, or don't call into this until the soup Nazi has given soup to at least one more customer, or there's 3 people in line at the soup Nazi place, right? And we want to make sure that at least one of them gets served before we allow another one in, is you use this dispatch semaphore wait. So this underscore frame, all we end up doing, so I called it a frame boundary semaphore. That's actually just a, okay. Right. So we're actually going to use this too. So this will be another method on our MTKView delegate. Configure. I just call it configure metal. And so all it does is it just it sets us up so we can create this this dispatch semaphore, right? So we just create the semaphore once, and then it kind of keeps working for us. And this value k max in-flight buffers. So let's look at that. Where is that? Yeah, and that's just a constant. I just put it up here. Okay, so k max in-flight buffers, so 3 buffers at the same time. The buffers are, and this code, by the way, is actually, it's taken straight from one of Apple's example code things. And I just used that. I basically have taken their demos and just like made them like non-object oriented, or like used as many of the object-oriented, like the minimal parts of it, and then kind of stripped out the other stuff that I felt could be more procedural. So that's where a lot of this comes from. But K-max in-flight buffers is like, that's the number of customers you can have in line at the soup Nazi place, right? Or in this case, it's Vertex buffers that you can have in line, getting ready for the GPU to draw their contents, right? You can only have that many, right? So, and that's what triple buffering is, right? We say, wait a second, we're going to let 3 of these stack up before we allow another one in. Now there's another function that we have to call just to get this set up again. Dispatch semaphore there's dispatch semaphore wait, and then there's okay, yeah. So there's a lot to get into thinking here, but what I'm going to do is I'm going to take all of this here, and we're going to just, this will give us kind of the, yeah, we'll come back to that. We're obviously missing some variables. There's things that we have to set up first, but we nevertheless, I can kind of walk you through a lot of this stuff just so you understand it. But what you'll see here is we have this, we're going to use a completion block, and we're going to have that completion block then, oh yeah, so we're going to have this completion block happen after our drawable has been presented. So when so what ends up happening is inside of MTKView you have the current frame that's being drawn. That's called the drawable, right? And then what we're going to end up doing is we're going to present that drawable with the updated graphics buffer, and what we want to have happen is at the moment that that new drawable has been presented, that is the moment when our when the customer has more or less been served. When we know that that buffer is no longer going to be read from, that vertex buffer, and that's when we know that we can allow another customer or another vertex buffer into that queue, right? So it's, you know, kind of to use that soup Nazi analogy, it's like there's 3 people in line at the soup Nazi place. This person gets their lobster bisque, another one comes right in. And it's right at the moment of checkout that the next one comes in, and now we can still only have 3. At the very start, we're going to have customer, customer, customer. Someone's going to get a lobster bisque, another customer comes in. It's going to be like that. And that's basically what's going on here. We got buffer, buffer, buffer. Someone gets served, another buffer, right? And that's dispatch semaphore wait says don't call the code from this line. Like don't call any of the code that comes after it. So none of this code is going to run until a customer has been served. If we have 3 people standing in line, right, or 3 buffers getting ready to be rendered, none of the code after this particular function is going to get called until one of those individuals, or one of those gets taken care of and drawn. And you can see that with the dispatch semaphore signal function, right? So this dispatch semaphore signal, what that does is that's the moment when we know the customer has been served. That's a way of telling the dispatch. That's the way of telling the dispatching system or the scheduler to then allow these people who are maybe standing outside in the cold, you know, waiting to get some lobster bisque. That's kind of when it's like, okay, you know, we can open up the doors to the soup Nazi place and like let people in, right? So we can let like one more person in so they can get a lobster bisque and not be cold. So that's what happens when you call dispatch semaphore signal, right? So when the frame is drawn, we then allow another one to come in and allow another one to be awaiting to have its buffer drawn as well. So what does this do? Ultimately, this creates a very smooth 60 frames a second kind of a game experience, or whatever the maximum amount of frames a second that Apple will allow you to do on their hardware. I think on this iMac and on most laptops, it's like 60 frames a second is kind of what they allow. So that's kind of what this does. And the way so that I hope was a fairly good explanation of it. At this point, there's maybe a few more bits in here because the problem with a lot of this code is like it's this idea of there's kind of a lot of other parts that you have to understand in order to sort of know what this is doing. So this command buffer thing, I have not yet explained what that is and how we get one. I'm kind of working backwards here, starting from what the process of drawing frames is going to look like, to then ultimately, you know, setting up all the stuff before we actually do it. But what you have is you have a thing that will schedule the draw call with the current vertex buffer and texture data, and then when that thing is finished, it will signal. So that's what this completion handler is, right? So it's going to present it, and when it's done presenting it, then this code is going to get called. So whenever you tell a command buffer to present a drawable, it's not going to present it right away because this is vertical sync, right? So vertical sync is just, what that means is the contents of the screen get drawn roughly at the refresh rate of the monitor. So if you've got something that needs to get drawn, you don't want to be writing to that buffer at the same time that it's getting drawn out. You want to only be writing to it before that, at a time when it's not being drawn. If you don't do vertical sync, then you get things called screen tears. What a screen tear is it's like when half the screen is drawing stuff from the previous frame and the next half is drawing stuff from the next frame. So if you want to have vertical sync, what that means is that when you tell this command buffer to present the drawable, it's not going to do it right away, right? It's not going to do it immediately. What it's going to do is it's going to schedule it so that it happens at the refresh rate of the monitor. That's kind of how that's going to work. So right after it's done that, that's when we signal the semaphore to allow more work to continue to happen, to allow another frame buffer to pop into that little small queue of like 3 of them. So now that we kind of understand that idea, and of course if we try and compile all this, there's a bunch of stuff that we need to have. So we need to kind of get into that. So let's well, I think what we'll do is we'll actually just we'll kind of go backwards from some of these things and get to, I want to just show you how to look through the documentation to figure out some of this stuff on your own. You sort of have the advantage of, I didn't really have like a good example like this when I initially started, something that would just go through and like show the dispatch semaphore and how all that works. So this one bit right here was the hardest part for me to get right. So now that we've got that figured out, we can actually start looking at the documentation and kind of look at, okay, what, like let's look at metal kit present drawable. What's that? What's the deal? We may not find that. We may have a hard time with that one. Present drawable. End encoding. On-screen command buffer. Okay, so we're definitely going to need an MTLRenderPassDescriptor and on-screen command buffer. I'm not really sure what. So again, let's look at MTL. Let's see if there's such a thing as an MTLRenderPassDescriptor. There's render command encoder. Okay. I'm just crawling through the documentation. Render command encoder, object by calling of the MTLCommandBuffer object in which you want to encode rendering commands. Okay, so here's kind of an overview of what we need to do. So this is from their documentation. To perform a rendering pass with a render command encoder, create an MTLRenderCommandEncoder object by calling the render command encoder with the descriptor method of MTLCommandBuffer object in which you want to encode rendering commands. So this MTLCommandBuffer thing, we need to figure out what the deal is with that. A container that stores encoded commands for the GPU to execute. Okay, that sounds good, but how do we make one of these? Don't implement this protocol. Instead, create a command by calling an MTLCommandQueue's object command buffer method. Okay, so to get the command buffer, we have to create an MTLCommandQueue. What's one of those? MTLCommandQueue, a queue that organizes command buffers for the GPU to execute. Okay, this all sounds good. How do we get one? Into order list command buffers for an MTL device to execute. You don't define classes to create command queue. Call the new command queue or a new command queue with max command buffer method of an MTL device object. Okay, so new command queue. Okay, we're going to look at this. Okay, so a new command queue object. Command queues are always associated with the originating device. Okay, so we're going to copy that thing. And now remember, this is an MTL device. So there's a little bit of kind of funky passing things around that we're going to have to do. So remember this MTL device thing, right? Well, this MTL device is actually going to be the thing that creates the command queue for us. So we need to make a command queue, right? And then we're going to have that so we'll see how that works. New command queue. So we have an MTLCommandQueue, right? Okay. Now notice that I did not create this in the draw in MTKView method. And the reason I didn't do that is because this thing right here needs to be like, I'll just say it's important. Like, this needs to be really, really fast. It needs to be like super fast, because if it's not fast, then well, you're gonna have drop frames and bad performance. We can't be allocating anything inside of here, or if we do allocate stuff, it needs to be only the things that Apple requires us to allocate or to deal with. You don't really want to be doing anything that's going to be doing much with memory or creating. You don't want to be creating new things. To as little as possible, you need to be doing those things. So that means that we would need to instead pass an instance of this command queue here over to this MTLKitView delegate object. So we need to get that from outside of the main game loop right here, right? And we need to get it from here over to MTLKitView delegate, and we can do that. I believe it is at property, and then we just need to like specify the type, and the type is MTLCommandQueue, right? So we'll set that as the type. Call it just command queue. Okay, and then now we should be able to just set that. So we'll just say, we'll just say MTLKitView dot command queue equals command queue. I mean MTLKitView delegate. So we got that. We'll just set it. You can just use like regular property stuff when dealing with those object-oriented things. So, all right. So we know we need to make this command queue thing, right? So let's go back to where we were. MTLCommandQueue. So we have this thing, and then to render images or execute computer operations, use the command queue to create one or more command buffer objects. Then encode the command into those objects and commit them to the queue. So MTLCommandBuffer objects, that's what we really need, this MTLCommandBuffer. By calling MTU's command buffer object. Okay, so let's look at this command buffer object. This method returns a command buffer that follows normal memory management conventions and holds strong references to objects such as buffers, textures, sample, and state objects that reference created by this command buffer. Okay. If The command queue has the maximum number of command buffers, and the app already has that many buffers waiting. This method blocks until a buffer becomes available. So we're not actually, I don't think we're worrying too much about that. So the thing I want to say that there was, I want to see if there's any rules. This I kind of can't remember if from my other games. I want to say there might have been some rules about when we can use command buffer. So I just want to like look that up. Yeah, okay. Right. So we definitely need to create the command buffer on the rendering pass. Okay. So I think what we do is inside it, so we pass the command queue over, so we created that thing, we instantiated that. And what we need to do to create this command buffer is inside of a single, so remember this draw an MTKView function or method, that represents like a single frame that's going to get drawn. And inside of this dispatch commands, that's where we're going to be doing all of the drawing. So at some point, we're going to need to make a command buffer. So I'm just going to yank that. I just hit Y. We'll get into auto release pools and what they are I can kind of touch on that really quickly. Basically, one of the things that you can use in Apple land or in Objective-C is you can use a thing called an auto release pool, and basically what it does is if there are object-oriented stuff, if there's object-oriented stuff that gets allocated inside of the braces of an auto release pool, at the very end of this brace, once the execution hits that, then anything that can be freed up, any object that can be freed up will be freed up. I don't really use many of these, or I only use this in a few very specific ways because I don't actually have a lot of object-oriented code. What ends up happening is I'll use this just on what I would call hot loops, or like loops that get run a lot, and in places where I'm sort of forced to deal with object-oriented code, which is the case here. So just in order to use Metal, we got to use some of this object-oriented stuff, and that means that we have to be a little bit more careful about making sure that their dynamic memory allocation sort of system for objects will clean up after itself. There actually isn't a lot of allocations that go on or that are used inside of the drawing of a frame, but there are actually some. And if you don't, this is not great design if you ask me, that like we have to be, we have this possibility of objects leaking memory on every frame if we don't put this in. That to me seems like kind of a shaky thing and probably not such a great design. Because I don't have that problem on Windows, if I can tell, and I don't actually have that problem when working with OpenGL either. So like kind of forcing people to use object-oriented things just to like draw a frame, and then possibly having those things leak memory on every frame call that seems like a bad design. But what do I know? So. We have this command buffer, and we're going to create a new one on every frame, and then we're going to use a thing called we'll get to it soon. A thing called MTLRenderEncoder. It might be render command encoder, yeah, render command encoder, let's call it that. And what that does is it actually then gives us specific rendering commands to tell it to execute. Maybe we could try and get to like a clear color just by the end of this one. So let's see if we can do that. Well, I would like to actually do that. if we could get to just something where, and to get there, I'm going to kind of use some of my previous code here. So, yeah, MTL render command encoder. Whoa. Okay. Command buffer. Yeah, so I think in order to create one of these, so we have the command buffer, and then we can use the command buffer to control when the drawable gets presented. And then I think we also need to create one of these things called an MTLRenderPassDescriptor. I don't actually do a lot with that because I only ever do one render pass. So a lot of this stuff, I'm just showing you, hang on, I'll take some of that, I'll take that render command encoder. Yeah, okay. Oh gosh, there's actually a lot more that we're gonna have to do here, but that's fine. I was hoping we wouldn't, yeah. I want to see where the clear color. Oh yeah, we could actually do the clear color on the render pass descriptor. Okay, maybe we could do that. I don't know, just like show a different clear color. Let's try that. See if that gets us anywhere. We can touch on MTL render command encoder later. But I want to see if we can just do like do our own clear color on that, and then see what happens. So yeah, that's the clear color. So I'll tell you a few things about. Yeah, it seems like in order to do what I'm recalling now is MTL render command encoder. You have to create one of those. You have to let it know what the viewport is, which we haven't really set up. Come to think of it, I'm honestly not sure if any of this stuff will work if we don't have a render command encoder. So it's probably not gonna. Yeah, it's probably not gonna work if we don't have that set up. So let's just set one of those up, and we'll kind of go into that. Although that kind of means that we need to talk about render pipeline states, and well, maybe not. Maybe we can just end the encoding and see what happens. I've never actually tried any of this stuff without, what I don't know is like, if you just end the encoding, will it just draw like the clear color? I don't honestly know if that will happen. So this is a very high level thing. So like a lot of times if you go and you look at Apple's documentation or you like use their example code, the problems I have with it, oftentimes, first of all, it's very like object oriented, which means that all of this stuff is like separated into like this little method call over here and that like and this little one over here and that little thing over there. It's like chopped into bits, and you don't actually get a good holistic picture of what's actually going on, which I don't like. So what I'm trying to do is give you that holistic picture in case you're trying to follow along and having a hard time, as I was. So there were a few questions that I had when I was looking through their documentation, looking through their way of doing it, and foremost among them was, all right, how many render pass descriptors do I need? Do I need one? Do I need two per call? Because that's like a thing. You can do multiple of these or not. Generally speaking, the answer to that question is you only really need one. How many of these render encoders do I need per, if I just want to draw like a triangle on the screen? Well, again, probably only one. You only need one. And what you're going to do is you're going to use this render encoder to you're going to like swap out different shaders and different vertex buffers and different So a thing that's basically just like shader/vertex buffer, that in Apple land they call that, or in Metal they call that a render pipeline state. So you'll swap out the pipeline state. We'll talk about that. We'll actually set that up. But basically, you're only ever going to use one render encoder, and most of the time you're only going to use one render pass descriptor, just to do basic drawing, which is kind of what this is. If you start getting into some of the more complicated kinds of scenes that you could do, then presumably you could have multiple render pass descriptors and multiple render encoders. But really, for the most part, you're just going to have one. So yeah, let's take a look at this. This is probably going to be wrong, but we'll see what we can do. So let's just try for our clear color, like no red. Let's just go for green, right? So we'll do all green. Right? No, is it 255? I think. Right. And then no blue. Actually, I think we just want we'll just do one. And no blue. And then alpha of 1. So we'll just do that. We've got the current render pass descriptor, right? And then we've got, so you can do these load actions on a render pass, which is like at the start of this render, let's just clear everything that was previously there. And then we'll set a clear color. In this case, we're just going to set it to green. And then we're going to create a new render pass descriptor, and you don't even have to set the label. I don't really care. This is I'm not going to set a label because we don't need it. That's for debugging purposes, which we'll get into. I actually really like the way that Apple has done the metal debugger, and I kind of wish that other companies would follow suit. Playing around with it in Visual Studio recently, I haven't quite loved that as much because you have to like download a separate tool or whatever. So, and the only thing we need to do is set the viewport. And I think, could be wrong, this I'm not really sure. So we have to look up MTL viewport. And I'm just going to be real quick about that. MTL viewport. It's a struct, origin x, width, height, z near, z far. So I'm just going to do 0, 0, 1024, 1024. See what that gives us. It's probably going to be wrong, but you know, we'll just see. And that's a viewport. Now let's just see if, like, can we compile this? Typing too fast. Oh, all kinds of problems. Use of undeclared okay, frame boundary semaphore is not defined. This is going to take a little bit longer, so bear with me. Right. So we need to have a property, I think, that is on MetalKit view delegate. So at property. I forget how I did that actually with semaphores. It's a dispatch semaphore. I don't, again, you know, because I don't really use much of this stuff that often. I tend to forget how to do so. Let's just look for frames. See how I did it before. Oh yeah. So I set that up as like a local. Okay. I'll explain some of this stuff. Yeah, and we're also going to want this current frame index. So that's okay. So this is not this code is not exactly going to be properties that we actually. So in Objective-C, you can have a thing that's called a property that's kind of like an outward-facing thing on an object. That kind of goes back to that cell metaphor, right? Of like cells have channels and like some stuff can get into the cell barrier, and that's what setters and getters are kind of trying to do. And so you got to use the channel to get into the cell. With Objective-C, you can also create kind of like this internal state representation, like state that is not accessible outside of the class, aside from a few functions that can get at it. And in this case, the frame boundary semaphore and current frame index are things that you can use. So that's actually what we're doing here. So we're going to have these dispatch semaphore is created as kind of internal state that other things that are interfacing or talking to this object do not ever touch. So it's like private state, right? And the only reason I'm doing that is because like we have to, because it's object-oriented programming that we have to use to do the other stuff. So we've got that set up, and then we need to call this configure metal on it, right? So because what that does is it sets us up to create the dispatch semaphore and to set the current frame index. So we're going to do that. We're not actually going to use the current frame index quite yet, so we'll just call this configure metal on MTLCommandQueue delegate. So now we've got some stuff. Let's run, see where we get. Command buffer. Did we never create the command buffer? Wait. No, assign, retain. Assign is assumed. Okay. Oh, that's a warning. All right. That's probably okay. Default assign not appropriate for object. Oh, I guess that's not allowed. Okay, so I think we need retain. Yeah. So retain, I think, just means like hold on to it by reference. Assign by reference. Is that how you do it? Yeah. I don't remember all these rules too well. Or is it this? Yes, it's this. You have to put little, okay. So the command queue is actually a pointer to something that was created before, like it was created at initialization. We create this command queue here with new command queue, and then we set it as a pointer on MTLCommandQueue delegate. Assign would be for types that are not reference types, so types that don't do any allocations, like just variables, like you know, like integers or that kind of stuff. So let's see if that gets rid of that problem. Soldiering on. Command buffer. All right. So maybe we did not get the command buffer. I thought we had the command buffer. Command buffer. We have it here. Oh, but it's not inside the auto release pool. Do we need to put this all? I forget if I ended up making that choice. I want to get it right. So if I ended up putting that in the auto release pool. Yeah, I think all of this stuff, all of the actual drawing happens inside of this auto release pool block. All right. So it isn't just this part that's inside the auto release pool. Basically, I don't want to leak any memory from like objects inside of drawing one frame, and so we put all of it inside an auto release pool. That's my way of doing it. including the scheduling of it, of the actual presenting the frame, all that stuff. So this is just kind of like automatic memory management for any objects. There's not going to be too many of these. And then inside the actual frame, we're not going to do any allocations or deallocations or any of that stuff. So it's just this is pretty much the only place in my Mac platform layer where I'm doing any kind of like fretting about, you know, what memory might be allocated or not from object-oriented stuff. There's really nowhere else in my code that has to care about any of this stuff. And you'll see why later. So let's try it. Let's run this. Okay, getting better. CommandQueue not found on object type MTLKit view delegate. Really? I thought we had the CommandQueue. That is a property. MTLCommandQueue at property. This is happening line 118. Property CommandQueue. Interesting. Why would that not happen? Do I need to do something stupid like set CommandQueue? I don't honestly know. Set CommandQueue. Warning class. Oh, that's right. Okay, yeah, so right. Duh. There's the difference between something that runs on a class and something that runs on an instance of a class. And the way that I had my naming of this was kind of, it wasn't totally clear what was the class, like metal view delegate, the class, the higher level thing, versus just like one instance of the class. And so these are instance methods that we're using. And so we want to call it on the instance, which is just this one view delegate. God, you know, it's so funny getting back to some of this stuff because like this, yeah, there's just so much more to deal with or to worry about in object-oriented programming than when you're not using it. It's very apparent. So now we can build it. Draw in MTK view. So this is a linker error. So this linker is saying that draw in MTK view was not found. So I'm guessing that if we look that up, a lot of times when you get those, an error that looks like, you know, undefined symbol for architecture, that's typically a linker error. And what that means is we didn't link with the dynamic library or a framework that has that in it. And so I think that's because we didn't link with MTLKit. We linked with metal, but not MTLKit. So we just need to change our build script to link. Come on. Tutorial. We just need to change our build script to link with MTLKit. Yeah, you see metal? We got dash framework metal. Don't have dash framework MTLKit. Okay, what now? Symbol's not found. Huh. Undefined symbol. Oh, could that be? Is it metal that's not defined? Wait a second. Yep. Oh, wait. Oops. Wrong one. Or is it? AppKit, MetalKit, metal. Where is this? Yeah, this is North. Okay. Hang on, I'm just gonna check my other, see what I did in that one. Okay, I definitely included metal. This one doesn't have metal in it. So that's probably where I'm guessing that's where it's coming from. We linked both libraries. Okay. Undefined symbols for architecture, GXX personality, MetalKit view delegate. GXX personnel. Personnel. Oh, I think that's right. So in order to do dispatch semaphores, there's some other thing we have to include. And I don't quite remember which of those it is. Yeah. I know that we need some, so basically what it comes down to is one of those things for dispatch semaphores is in another library. I just don't know which one it's actually in. I think it's probably in one of these like mock, if I was to guess. Okay, I won't upload my video. We have such like terrible internet connection here. It's kind of like, all right, does this work? What do we got? No, still not found. Undefined symbols. GXX underscore GXX personality. Oh, there was something I did. Now that I remember, I keep forgetting how much stuff I have, put into this that are like problems that I've solved that it's like I solved it and then I forgot that I solved it. This is one of those. I think, is this, yeah, I think we need to add the standard library in the compile flag. I think that's what it is. So that's actually something where, let's try -L std C++. I know that I have that. Hey, it worked. Okay, so yeah, that's -L std C++ is what gives us. So I think that gives us a standard library, which allows us to create these dispatch semaphores. I have no idea what this is going to do, but it may, in fact, give us something here. It may give us the clear color. That would be pretty cool. So we'll see if that actually happens. If it's green. Oh, it's green. Okay. So that's neat. And that's kind of getting us to the start of something, right? So the fact that this is showing up as green tells us some things. It's kind of an indicator that we have succeeded, at least in some respects. And I'll kind of go over that with you. Right. So we have succeeded in, at the very least, drawing something into this view using metal. It's not a fancy version of metal at all. We're not actually drawing any kind of geometry or anything, right? All that we're doing is we're doing one render pass. That's with this render pass descriptor thing here. And we're drawing the clear color. The clear color is just like, that's the base, that's like your base coat of paint when drawing a frame or a scene or anything, and then you draw on top of that. So usually what you'll do is you'll draw like a clear color that's like, the color way in the far distance or something, or that's the background. And then stuff in the foreground will kind of match it. And what it does is it prevents you from having to like do one big draw just of that same color with like some geometry. So we managed to do the clear color, which is like a green. That's cool. And aside from that, we haven't actually set it up to do any geometry, or we haven't set up any vertex buffers or any of that stuff. But we did get some rendering working inside of our MTLKit view. So we've kind of got the basics of we got the start of triple buffering, and I kind of explained to you how that works with the soup Nazi metaphor. So remember that triple buffering is we're going to manage 3 vertex buffers at the same time. Typically, the vertex buffer that is being written to by the CPU is going to be a different one from the one that's being read from the GPU at the same time. So we want 3 of those so that those 2 things aren't happening at the same time, right? And we use a dispatch semaphore, which is kind of like the soup Nazi place, where like only 3 people can get in line, or like the soup Nazi gets really mad, and as soon as like another customer is served, then another one can get it. You know, they're waiting outside, they're kind of peering over and like, oh, I hope we don't piss them off by, you know, having too many of us in line for soup. So then as soon as someone sees a customer get out, then they go in, and you know, in that case, the customer is actually just a frame that's being drawn. So we can never have more than 3 of these draw commands kind of queued up at the same time or ready to go. And what that does is it ensures that the geometry that we're drawing is the most recent geometry, right? You can imagine what would happen if we allowed like 50 people to line up, or like 50 frames to line up. Well, maybe by the time we've processed these, you know, the ones that are lining up way in the back are very, very old. And so by the time we got to them, what I think you would notice is there'd be a lot of latency between input from the controller from the player, because things can just stack up indefinitely. So you'd probably also run out of memory, I would have to imagine. You would run out, well, would you run out of memory? Well, yeah, because something's got to like actually store the, I'm trying to think if that would happen. Yeah, something's got to store that thing to get executed, right? So if we're allowing this system to have, you'd probably trigger some kind of out of memory exception or something like that, because you can't tell Metal to like draw that many frames. You can't queue up that many. You couldn't queue up like an infinite amount of commands to the GPU. Eventually you'd run out of memory. So that's why we have that dispatch semaphore, is to only allow 3 at the most before another one can come in. So, and the reason we do that is A, memory constraints, but B, we also want them to be the most recent. We want to wait until one of those is drawn, and then call this code inside of this draw loop at a more recent time, so that the input is closest to the recent moment by the time that it does eventually make it to the screen. So you want to have like low input latency. So that's my best way of describing it. So we got that. We've actually got the basics set up for Metal. And now what that means is we can start talking next time about setting up a vertex buffer and then drawing some solid colors into that vertex buffer. So maybe what we'll try and do is like draw like just a triangle, like one triangle, and then we'll try and draw like a rectangle. And then we can start talking about moving the rectangle around inside of the space of the screen. And once you've gotten there, you've kind of started to get to most of what you need for a 2D game. We can start talking about then how to map the screen's coordinates to the game world's coordinates, so that when you're talking about drawing something in game units, it's like roughly the same as screen units. So there's a little bit of fancy trickery we got to do there on a 2D game. But yeah, you know, basic rendering setup. So anyway, if you enjoyed this, if you found it useful, subscribe, give me a like. I will post the code under day 6. Yeah, this got to be kind of a long one, but I feel like it was worth kind of pushing a little bit further. And gosh, subscribe on Patreon and all that fun stuff. I could, I don't currently have a job, so, I could use your money. It would be nice. Just something to consider. See you later.